Okay, thank you so much. So good morning, everyone. I'm Helvi Witek, and as Tom just said, I'm an assistant professor at the University of Illinois and an expert in gravitational wave physics, modeling strongly gravitating system, black hole binaries, with applications that go from, astrophysics to cosmology and high energy physics. So this week, I would like to give you a little bit of an overview, a bit of a taste on gravitational waves, what they are, a bit of the mathematical tools that we need to describe them. And on Friday in the last lecture, I also hope to give you a bit of an outlook, where are we going in the next few years, in the next few decades, because a lot of new observations are actually coming up. So we are in this really lucky position that since 2015, we actually have observations and detection of gravitational waves that go hand in hand as a theoretical development. So I will start actually sharing my screen now, because I have a few notes, few administrative notes before we start the proper lecture. And I hope everything works, because I just noticed that my Notepad program decided to have an update just this morning. So I hope you can see the notes now. I should also say, if you have any questions, please ask. You can just interrupt me during the lecture. If you're more comfortable to put them in the chat, you can put them in the chat. Tom said he would monitor it. And I will also stay on after the lecture if you want to ask a few more informal questions after the lectures. Okay, so first things first, reading material. I've added a few textbooks, standard textbooks that treat gravitational waves on the wiki, that goes from classical textbooks to really recent ones. And this lecture will focus mostly on the gravitational wave chapters from Carroll's book on spacetime and geometry, a new book by Valeria Ferrari, Leonardo Gualtieri, and Paolo Pani that came out earlier this year. And then a really wonderful book is by Eric Poisson and Cliff Will on gravity from 2014. And on the wiki, I also added a few of the discovery papers, a link to a lot of the gravitational wave papers that I will mention as we go along in the lectures. The plan outline for our lecture is the following. I will start today with some introduction, and we will start off with, as I said, mathematical tools, and in particular, we will look at the weak field approximation in Einstein's general relativity that will help us to describe gravitational waves. And I will talk a little bit about gauge choices in general relativity that will help us write wave equations for the metric for these perturbations that will then allow us to study gravitational waves. Tomorrow we talk about the propagation of gravitational waves, how they impact matter and how that's actually used to detect them. And then, so let's see how I can make this work. So this is exactly this clunky part where my tool is new. So in principle, I should be able to now move this up here. So it's, oops. Okay, this is not good. Okay, so I would just want to go up. So on the second part, on Thursday, I would talk about how gravitational waves are generated. And then on Friday, I will actually talk about the energy that is emitted in gravitational waves. And as I said, a bit of an outlook for the future. Okay, so let's just see. This is really not good. Okay, so it seems that I can go like this. So a bit of note and notation on the very last bit, and I prepared all of this so that we don't have to write this down. All I'm going to talk about will be general relativity in 4 space-time dimensions in asymptotically flat spacetimes. And for everything that I'm doing, I will use Waltz notation, and in particular, I will use a signature that is mostly plus. So we use a minus plus 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 signature. and then the usual space-time and spatial indices. So bear with me as we go along. If that's unfamiliar to you, I would suggest just read it up in the standard textbooks. Okay, good. So with that, okay, I will practice it until tomorrow, I promise. So the first part is really the introduction, and I have a question for you actually. So what do you think gravitational waves are? So you can just unmute yourself and give your ideas. What do you think this is?
Small perturbations of the space-time metric?
Yein. So that's how we will treat them. But more generally, what do you think they are?
I just think an analogy to radiation that comes from an accelerating charge system, basically the radiation from accelerating sources of gravity.
Yeah, that's excellent. Any other ideas? Okay, so Kelly already hit it to the point. So if you do take the analogy to, for example, electromagnetic radiation, where electromagnetic waves carry the information about dynamics of charged systems, then you can think of gravitational waves as changes or information about changes in a mass-energy distribution. What is unique to gravitational waves, however, is that we describe, or that it turns out that they are actually waves or changes of the space-time metric itself. Or in other words, gravitational waves are actually metric waves of the space-time itself, not just something that propagates in a space-time, even though that's what we are going to treat them as, but in general, really they are waves of this medium in quotation marks space-time itself. Yeah, so let me write that as one of the first notes here. Sorry, this should now go here. So in the first item, what are gravitational waves? So as I said, they describe changes in the mass energy distribution. Oops. Yeah, and they propagate as gravitational waves. And let me just use GW as abbreviation for gravitational waves. They are actually metric waves. Oops. That is, they are waves of space-time itself. Okay. Or in other words, they indicate essentially a change in the proper distance between points in space-time. Yeah. Between points in space-time. And let me abbreviate space-time as ST. Okay, next question for you. What are typical sources for gravitational waves? So if you think about, recent press releases, information that you may have seen, what generates gravitational waves that are strong enough that we can measure them here on Earth or close to Earth?
Binary black hole, binary neutron star black hole.
Mm-hmm. Okay, can you think of anything else?
Supernova?
If they're close enough, we would actually be able to measure gravitational wave signal from supernova explosions or core collapse supernova explosions. Anything else?
Primordial gravitational waves.
Okay, so there are a couple of more that I could think of, and that list is probably still not complete. So if you think about a neutron star, a rotating neutron star that is not perfectly spherical, so if you have little mountains of on the surface of those neutron stars, they actually create a quadrupole moment, which means that they generate gravitational waves that are potentially observable as well. And then in the future, we are also looking towards measuring or searching for gravitational waves from what we call an extreme mass ratio in spiral, where a star or a small stellar mass black hole orbits a supermassive black hole like the one in the center of our galaxy for many orbits, which we hope to measure with future instruments in space. So these are all typical sources that generate gravitational waves. So let me just notify that here. So we already heard, oops, that's supposed to be black hole plus black hole, neutron star plus neutron star, and a mix thereof. Then we talked about neutron stars or mountain on neutron stars, core collapse supernovae, talked about stochastic and primordial gravitational wave. Etc., etc. Okay, and then I prepared this slide here to tell you a little bit about breakthrough detections that we have. So one of the sources that is really relevant for the field of gravitational wave astronomy is listed here under GW 150914. So that stands for gravitational wave event measured on the 14th of September 2015. And what we had here, what we detected here, were the very last orbits of two black holes, one of which had a mass of 29 solar masses, the other one 35 solar masses that orbited around each other, merged into a final black hole of 62 solar masses, emitted gravitational waves that we detected here on Earth, and that carried an energy of about 3 solar masses. These 3 solar masses, if we convert that to more conventional units, essentially carry an energy of 10 to the 35 terawatt hours. Just for comparison, what we use here on Earth per year is about 10 to the 5 terawatt hours. So that's the orders of magnitudes that we're talking about. And the gravitational wave was emitted in a system 440 megaparsecs away. That's about 1.4 billion light years. That is, this gravitational wave signal that we measured 5 years ago was emitted about 1.5 billion years ago, when here on Earth, the first multicellular organisms just started to develop. So I still find that absolutely mind-blowing, and it's so important because it really changed our field of gravitational wave science. So let me just add some of these specs here. Of course, you can always come back to that later on. So as I said, we had 2 black holes. So this was a black hole plus black hole binary with a system of 29 solar masses, oops, M solar plus 35 solar masses going into a final black hole of 32 solar masses plus gravitational wave energy that was the equivalent of 3 times the mass of the sun times the speed of light. The distance, as I said, was, let me just take this, so 1.4 billion light years away. And the amplitude the strain that we measured here on Earth was still extremely small. So even though this gravitational wave carried about 3 solar masses worth of energy, the amplitude, or the relative amplitude, that we call h, was 10 to the minus 21. So this is a relative length. So if you think about the detectors that we have here on Earth that have kilometer size arm lengths, we were trying to measure a change in that arm length that was 10 to the minus 18 in comparison to that. So this, again, I think is a feat in engineering and really mind-blowing as well.
I have a question.
Just go ahead.
Was there like approximation of like how much of the I don't know how to say, like when the black holes were, before they collided, how much of the energy was radiated away?
Okay, so no, that's a very good question. So so what we see here in the picture is essentially the signal that we've measured the last few orbits, and these essentially contained most of the energy. So most of the energy was here emitted during the merger. And actually, so if you're interested in the inspiral, in the part that goes up to the merger, that's exactly what we will talk about on Friday. So how much energy was emitted in that part. But yeah, so the peak energy is really around the merger. So that's the most part. Does that answer your question? Or
I understand better, thank you.
Okay, very good. So next event. So which other event do you think was really important in gravitational wave physics? Do you remember? Okay, so I see a few questions. So if you think back to 2017, August of 2017, the following happened, and I've brought you a little cartoon here to illustrate that. So we had 2 neutron stars that, started dancing around each other, coming closer and closer, getting faster and faster and faster. And actually that signal, about 40 megaparsecs away, was measured here on Earth by the gravitational wave detectors LIGO in Hansford and Livingston in Louisiana, and not in the gravitational wave detector in Italy. So we actually could pinpoint where the signal came from. So we measured a gravitational wave signal from the late inspiral of 2 neutron stars that merged. We didn't see the merger, but the gamma ray telescopes, Fermi and Integral, they observed a short gamma ray burst that was associated to that same event. And a few hours later, we observed optical, infrared, and radio signals from that same event that could be associated to a merger of 2 neutron stars. And that was the very first time that we observed an event carried by both gravitational waves and electromagnetic waves. So we call that a multi-messenger event that again opened up new areas of research. So down here below the comic, you actually see on the left the gravitational wave signal. So we see here the frequency versus time evolution in the late inspiral, where the frequency of those inspiraling neutron stars, so the gravitational waves from those inspiraling neutron stars increases over time until they're very close to merger. Then this gamma ray signal seen here in the middle plot was measured less than 2 seconds afterwards. And as I said, in all the rest of the electromagnetic spectrum, we could see signals from kilonova in the evolution after the binary neutron star merger. And again, let me just add a couple of specs here to this system. So that was a neutron star plus neutron star gravitational wave event with a total mass of about 2.8 solar masses. We actually cannot infer accurately the individual masses. So depending on how fast the stars themselves spin, there are actually quite large error bars on what their original masses are. The distance or the origin could be associated to a galaxy that is called NGC 4993. So that was about 40 megaparsecs away. And the signal lasted for about 100 seconds within the LISA sensitivity curve. That is, we could see about 3,000 cycles of these neutron stars. Okay, so just looking back at the rest of these 5 years, I brought you the chart of gravitational wave observations that we have so far. So these measurements, or this is a catalog of the measurements that we had since 2015 with the LIGO detectors. You see here the black hole gravitational wave events in blue that really cover a large mass range. So here on the y-axis, you have the masses of these objects in terms of solar masses, with the heaviest really going up way above 100 solar masses, which we hadn't expected before. So that really goes into the realm where we think about intermediate mass black holes that may be the origin of supermassive black holes that are hosted at the center of most galaxies. We have in purple, you may see that candidates of black holes that we already knew about before LIGO. So essentially here we have seen X-ray radiation from matter around a stellar mass black hole that's falling into the black hole and emits X-ray radiation. So these are the black hole candidates. And then in orange, we have two neutron star plus neutron star events merging, one of them the multi-messenger event that I just mentioned. Okay, so that's a bit about the sources. And the gravitational waves that we measure really carry, even though it's just a time series signal, carries information about all of these sources. What are their masses? What is their spins, their own orientation, their distance, where do they originate from? And I have another question for you. What do you think, where gravitational waves are important? Where do we find applications for them? What can we learn by measuring gravitational waves? What are your thoughts about this?
Well, we can test the strong field regime of gravity in a more direct way.
Mm-hmm. Yep.
We can learn about the composition of neutron stars.
That's right. What else? Okay, so I can actually think about a few other items. So we will learn about the evolution of stars before they become black holes and their distribution. We can learn about how supermassive black holes form, which allows us to actually learn about the very early universe, because with future detectors, we expect to see out to very high redshifts. We hope to answer with current and future observations the problem about the Hubble constant, because current observations are in disagreement, and this disagreement seems to become more and more significant. So we hope by measuring the luminosity distance, which we measure directly with gravitational waves, and by associating that to a host galaxy, to infer information about the Hubble constant. We already talked about neutron stars and the nuclear equation of state in a way that's completely complementary to, for example, heavy ion collisions. We also heard about testing strong field gravity, and I would actually take a step further where we will try to use observations of gravitational waves to infer or constrain extensions of general relativity that are inspired or motivated by quantum gravity paradigms. We tried to learn about particle physics. So that's one of the things that I've been doing over the last few years, so we can use black holes and their interaction with ultralight fields like axion-like particles to learn more about these particles that again is in a mass range complementary to traditional colliders. And we can try to learn and use that to learn about dark matter, which is another problem in fundamental physics. Where do these 80% of gravitating matter come from that we observe but don't know what they are? So again, gravitational waves may carry information about this as well. And then given the audience here, if you think about the theoretical modeling of gravitational waves, where, at least in a certain part, we would study the response of black holes to perturbation. So if we study quasi-normal modes, then this is actually a calculation that I think is also useful if you're interested in black holes and ADS. So that has no astrophysical implications, so we are not going to measure that, but the tools are useful to learn about the stability and response of black holes in anticitor spacetimes on high-dimensional spacetimes. Okay, so all that said, I think now we are actually ready to go and think more about the mathematics. Yeah, I said all of that. And what we want to do really, at least in this lecture, is try to solve Einstein's equations in a certain approximation. So let me go here. So let me start with chapter 2 here, which I label the weak field approximation and approximation. And gauge choices in general relativity. Okay, and as I said, the goal ultimately is to solve Einstein's equations and I will from now on abbreviate them as EE just to avoid writing that out. And we want to look for gravitational wave solutions. Yeah, so what we want to solve is this equation which has an Einstein tensor here on the left-hand side. That is the Ricci tensor minus 1/2 the metric times the Ricci scalar equals to a meta distribution 8 pi. And just for now, I will actually also write the Newton's constant and speed of light times the energy momentum tensor. Yeah, so we have our geometry here on the left-hand side and a meta distribution here on the right-hand side. Just as a note, so I'm not going to write out what the Ricci tensor is, but this is our Ricci tensor that describes the space-time curvature itself. G mu nu is a metric, and T mu nu is our energy momentum tensor. Okay. From now on, I will use geometric units unless I find it useful and instructive to reinstate all the natural constants. So from now on, I will set Newton's constant to 1 units. And I will set the speed of light to 1. Yeah, so we will not see any of these factors in our equations, and I will reinstate them when we need them to actually, make connection to observations. Okay, so to solve Einstein's equations, we have, of course, different techniques. If you think about systems that have a lot of symmetry, we can actually solve these equations still analytically. On the other end, if we do not have any symmetries, then this system of what's actually 10 coupled nonlinear partial differential equations, we need to solve them numerically. And that's actually what I do on everyday life, that I solve these equations using high performance computing to model the dynamics of black hole binaries in the late stages of their inspiral and merger with, as I said, applications not just in astrophysics. What we will do here, however, is take yet another approach where we say, okay, let's assume we have a weak field, or we have at least the smallest parameter in our system, so that we can perform an expansion around a background. So what we will assume here is that our gravitational fields are weak, that we are far away from the source, and that allows us to still perform analytical calculations. Okay, so that said, let's go to the next page. So we are, for the rest of today, talking about the weak field expansion, how to develop the formalism mathematically, so that we can continue tomorrow with looking at how gravitational waves actually propagate. So that is chapter 2.1, the weak field expansion. Oh, I'm sorry. So what we have here is the following system that we say, okay, we have some kind of source here. We're putting our detector, our observer, far away. Here, that is that the distance, we call that capital R, is much larger than the characteristic wavelengths of our gravitational wave, so that we can actually assume that we are sitting in a weak field. Okay, so the other assumption that we make is that our source, our meta distribution, is localized, is confined, and that the source is moving slowly. That is that, so for example, if you were to think about a binary system of stars or of black holes, they would be sufficiently far apart that their velocities are small as compared to the speed of light. Yeah, so our assumptions here are the following. Is that the gravitational wave source itself is a localized distribution of matter, that they are slowly moving that is, the velocity over the speed of light is much smaller than 1, and we measure far from the source. That is, the distance, capital R, is much larger than the characteristic wavelengths of our field. Okay, so what we will do now is expand our metric, and we will choose a specific background. Here in particular, we will expand our metric around a flat space-time. that is, we will set our background metric that I in general would call a G0 to be just the Minkowski metric. Or in other words, this will be a diagonal matrix -1, 1, 1, 1. Okay, so that is, we write our metric, our general spacetime metric as our background metric, so the flat metric, plus epsilon times a perturbation h mu nu. So my notation here is that h mu nu is much smaller than 1 as a perturbation. I use epsilon as an order parameter to keep track of my perturbations. I will also so I will also do the following, because our field h mu nu, our perturbation, as a perturbation, we can actually treat it as a tensor field in our background. So we treat h mu nu as a tensor in our background metric. That is, and now I will continue here on the left, that is, I will use the background metric eta mu nu to raise and lower indices of our perturbation tensor h mu nu. Yeah. So in particular, if I want to write our inverse metric, inverse perturbation h mu nu upper indices, then that would just be applying the background metric eta mu nu with upper indices mu rho eta nu sigma on our metric on our perturbation h rho sigma. That approximation also means that we can write our inverse spacetime metric and the following. That the inverse metric g mu nu with upper indices can be expanded as eta mu nu with upper indices mu nu minus epsilon times h mu nu with upper indices plus plus higher order terms of order epsilon squared. I'm not going to do the calculation here, but you're very welcome to check that at home, that this is correct and gives you the right properties. Okay, so next, let me just write out the curvature tensors in terms of our metric perturbations. I'm not going to do the calculation here. Again, if you want to see that in more detail, I recommend you do the calculation at home. So just okay. No. So the curvature tensors, and this will really just be a list of objects. So the first one is a Christoffel symbol. And it turns out, if you insert our metric expansion, that you can write the Christoffel symbol capital gamma rho mu nu as 1/2, and this is actually of order epsilon, eta with upper indices rho sigma times partial derivative d mu acting on perturbation h nu sigma plus d nu h mu sigma minus partial sigma h mu nu. And just for completeness, so by partial mu, what I mean here is a partial derivative with respect to our coordinate x mu. Okay, the Riemann tensor can then be expanded as follows. Again, this is a quantity of order epsilon. So Riemann, all lower indices, mu, nu, rho, sigma is equal to epsilon times, and then we have partial sigma, partial mu. I'm going to antisymmetrize over mu and nu, h nu rho minus partial rho, partial, and again antisymmetrizing over mu and nu, so partial mu h nu sigma. Okay, good. So contracting that gives us a Ricci tensor that we will use here. Oops. So, yeah. Okay. So the Ricci tensor again will be of order epsilon, and in terms of the perturbation is given by 1/2 epsilon, and then we have 2 times partial sigma, partial, and now symmetrized over mu h nu, so symmetrized over mu and nu, and then we have here an upper index sigma on the perturbation minus partial mu, partial nu acting on the trace of our perturbation. I will write down the definition in a minute. And then we have minus the D'Alembert h mu nu. Okay, so let me just add the definition to our box that we have up here. So h is a trace of the metric perturbation. So this will be eta mu nu acting on h mu nu. And the D'Alembert here will be exclusively the flat space D'Alembert unless I explicitly say otherwise. And that's because we're perturbing around flat space. And I don't want to carry around an eta all the time. So here our D'Alembert is a wave is given by eta mu nu with upper indices, partial mu, partial nu. Okay. So yeah, almost done with just setting up everything for our calculations. We actually find it useful to use, instead of this perturbation h, the trace reversed version of this perturbation h. And as we go along, it will become obvious why that is. So we will now introduce the trace reverse perturbation. Let me just go to the next slide for that. Okay, good.
Sorry, can I ask a clarification question?
Oh, yeah, sure.
This scalar h that you defined, is that h upper mu nu, h lower mu nu?
Exactly. So if you didn't see it, so I introduced the trace here. So this h.
Okay, sorry. Oh.
Yeah, so this is a trace of our perturbation. Exactly. And if you do the contraction, it's exactly h upper mu, lower mu. Yep, absolutely. Do we have any other questions? Okay, so if not, I will go. Oops. Okay, I apologize for this. As I said, so everything worked fine yesterday, and then this program decided to have an update just before our class, so that's why it's a bit clunky. I'll practice until tomorrow, promised. So yeah, let's continue. And as I said, it's going to be useful to look at the trace reversed perturbation. And that is defined as follows, that we say H bar, so that's our trace reversed perturbation mu nu, equals to our original perturbation minus 1/2 eta mu nu. And then we have here again the trace of our perturbation. And what you see is actually that now the trace of this new quantity, that is again the contraction of both indices with our background metric, is just equal to minus our original metric perturbation. Okay, and it turns out that this actually describes the gravitational potential that is relevant and useful to describe gravitational waves. Now, one last item is to write down Einstein's equations in terms of this trace reversed perturbation. And again, I'm not going to show all the details here. You can verify that at home. I'll just give you the final result. And here we can write, I should say, Einstein's equations in vacuum. What I'm going to focus on. So here the Einstein tensor becomes a wave operator, so the D'Alembert acting on our trace reversed perturbation plus eta mu nu partial rho partial sigma h bar rho sigma minus 2 times eta upper indices rho sigma, and then we have partial rho partial mu h bar nu sigma, and again we are symmetrizing over mu and nu here. Okay, so this looks still like a rather complicated expression, and we can actually use the gauge freedom, the coordinate freedom that we have in general relativity, to further simplify this equation. So yeah, so just to note, even though we look at Einstein tensor equals 0, is still complicated to solve. And we are still dealing with 10 independent components. So the question, of course, is, are all of these 10 independent components relevant, or do we have fewer degrees of freedom, and can we isolate those physically relevant degrees of freedom as we go along? And the answer is yes, we can. This is the part that we will do next. So, oops, independent components. And as I already alluded to, we use the coordinate degree of freedom to further simplify our problem, and in particular to identify the radiative degrees of freedom. Okay, and what we will actually see as we go along is that there are only 2 that we actually have to solve for. Okay, so yeah, that's good. So let me briefly talk about the coordinate transformations and the gauge freedom that we have in general relativity. So okay. That will be the next chapter. Oh, so we have now infinitesimal coordinate transformations. Okay. And in particular, we can consider the following type of coordinate transformations, where we say, okay, let's define a new coordinate. Let me label that as x prime mu, which can be which is given by our original coordinates x mu plus a tensor field xi mu. Then if we insert that into our metric in these primed coordinates is given by our original metric plus, when I'm writing this in this way, the covariant derivative mu acting on this generating vector xi mu, and we are again symmetrizing over mu and nu, and that generates a gauge transformation that is, this kind of transformation will leave the Riemann curvature tensor invariant. That means it will also leave our field equations, our physical degrees of freedom invariant. Yeah, so the curvature tensor and consequently also the equations of motion remain invariant. Okay, so this is a very general form. Let's now apply that to our weak field approximation, to our weak field expansion, to see how we can transform, how we can apply a gauge transformation to our metric perturbation. So this, yeah, I will go to the next page. Okay, good. So if we apply that to our weak field expansion, we find the following, that our original metric, of course, we had this expansion eta mu nu plus epsilon h mu nu. If we apply our gauge transformation, we can also write that as eta mu nu plus epsilon h prime mu nu, where h prime is now our transformed variable, plus 2, and again, this is of order epsilon, or that's the assumption that we are making here. And since we are in flat space, our covariant derivative become partial derivatives acting on our tensor xi nu. So if we compare that, that gives us a transformation for the metric perturbations. As follows, that our h prime mu nu equals to our original perturbation h mu nu minus 2 times partial derivative mu c nu symmetrized over mu and nu, and we would have higher order terms of order epsilon squared here. And then for the trace reversed perturbation, this will become the following, that h bar mu nu prime in our new coordinate system would be written as h bar mu nu minus 2 times partial mu c nu. And now we also have the trace part. So we have eta mu nu lower indices, eta, say, kappa lambda upper indices contracted with the partial derivative kappa c lambda. And again with higher order terms following up on that. Okay, so this is just a very general formalism for our coordinate transformations. So let's actually continue with making a few specific gauge choices that will help us solve Einstein's equations for weak gravitational waves. The gauge choices that I present are, of course, by no means unique, but they are very well adapted to the problem that we want to solve. Okay, but before I go there, I should probably stop for a minute and see if there are any questions before I continue with actual choices.
I'm curious, have people studied generalizations of this? Like, for example, the second order perturbation, or like the vacuum solution with the waves like passing through matter?
Oh, yeah, of course.
Okay.
Yeah, of course. I mean, I'm giving here a very simplified version of everything that's out there, just to give you the basic tools, because of course you can go to higher order and perturbation theory. You can also study, for example, different backgrounds. So if you are interested, for example, in the response of a black hole to perturbations of the metric or to perturbations of other fields, you would choose a different background metric. So yes, of course, there is, and also if you're interested in what happens if you have meta distributions, then you would extend that accordingly. So this is like a really, basic version thereof, and I think it's useful to understand the basic concepts. Right.
Sure. Thank you.
Okay, you're welcome. Do you have any other questions?
I have like a naive question. If we have a non-cosmological constant, then definitely the equations of motion of the metric perturbation H are all going to change. So which is the line where the change should occur first? Okay, so you saw, okay, so we wrote down the Einstein's equations with the perturbations, right? So if you bear with me, let me go back here, exactly. So you see here, I wrote down Einstein's equations in terms of the metric perturbation. And of course, here I assumed that we have vacuum Einstein's equations without a cosmological constant in 4 space-time dimensions. So this is a part that would change, right? So we would start with the equations that you're interested in and apply the expansions, the weak field expansion that we discussed, and then follow the math through, and you would get the equivalent expression of this. Right. Thank you. Okay, you're welcome. Any other questions?
Yeah, I have one question. Do we get any leverage from working in the Vielbein formalism instead of a metric formalism for these calculations?
That's actually a very good question. So let me try to see. So this particular calculation, maybe not, but there's one important calculation where we actually use a tetrad formulation, which is probably more closely to the Vielbein. And that is if you want to study perturbations around rotating black holes. So there's a very nice series of papers by Press, Tarkowski, and Badin in the early 70s, where they develop a formalism based on the Newman-Penrose formalism to calculate scalar, vector, and tensor perturbations around the Kerr black hole. Yeah. Okay. Any other questions? Okay, so if not, I would introduce a specific gauge choice that we make to further simplify the equations, the Einstein's equation that I've highlighted here further. Okay, and let me go back here. So, the first gauge choice that we make actually goes under the name harmonic gauge. And that is a choice where we actually have a wave equation for the coordinates itself. So since we're looking for wave-like solutions, that seems to be quite suitable to our problem. So we choose a wave equation for our coordinates, which is labeled a harmonic gauge. Yeah. Yes, it's adapted to our problem of searching for wave-like solution. And it is given by the wave operator acting on our coordinates x mu equals to 0. Okay, so one can now show, yeah, and we can, yeah, so one can show, I'm not going to do that here, that this is equivalent so this choice of harmonic coordinates is equivalent to having the contracted Christoffel symbol, that is this quantity here, metric, say kappa lambda, contracted with a Christoffel symbol mu kappa lambda equals to 0. And we can achieve that by choosing this vector xc that we've introduced before appropriately. I'm not going to do that here. And if we now take this expression in the weak field expansion, this can be written as the following. So this gamma mu can be written, again, coming in at our order epsilon, partial derivative, say sigma, acting on metric perturbation, mu sigma minus 1/2 eta mu sigma partial sigma and the trace of our perturbation. And this can actually be written in our trace reversed form, and that what makes it useful as the divergence acting on this trace reverse perturbation. So we have here partial sigma h bar mu sigma, and that, as we said before, was a choice equals to 0. Yeah, in other words, if you look at this very carefully, this actually, this last item here, so the divergence less property is actually something that we call also the Lorentz gauge. So what I'm just showed you, well, not showed you, but told you in a few lines, is that the harmonic gauge is also equivalent to what we would call the Lorentz gauge. And for that, I'm afraid I have to go to the next slide. So we've just seen the following. So the harmonic gauge, or equivalent to the Lorentz gauge, becomes this divergence-less property of our trace reversed metric perturbation equals to 0. And just as a side note, this is actually equivalent
to the Lorentz gauge that you may be familiar with from electromagnetism. Yeah. Lorentz gauge in electromagnetism, where you would have the condition that divergence of your 4 vector A mu equals to 0. Okay. Now, let's insert this gauge, this harmonic gauge, into our field equations. So if we do that, insert that in the Einstein's equations that we've written down before, and what we will see is that the Einstein tensor now becomes, well, we still had our box operator acting on our metric perturbation, plus, just to remind you, we had this eta mu nu partial rho partial sigma h bar rho sigma minus 2 eta rho sigma partial rho partial mu h nu sigma. And if you look at this very carefully, you should see that the second term is a divergence. So that goes to 0 in our gauge. And in the last term, you can shuffle around the indices to find that this actually gives you another divergence. So also this term goes to 0. So what we end up with is actually a wave equation, D'Alembert, acting on our trace reversed metric perturbation equal to 0. Yeah, that is, now we've reduced Einstein's equations to a wave equation for our metric perturbation. And that's something where we now start to have our techniques from partial differential equations, where we know how to solve these equations. We know how to solve wave equations. We love them, especially if we are interested in these time evolution and wave-like solutions. Okay. So let me just write this down because this is important. So as a note, so our perturbative Einstein's equations in the harmonic gauge become a set of wave equations for the metric perturbation. And the consequences of that are actually twofold. So first of all, this tells us that general relativity predicts the existence of gravitational waves. And that's by no means trivial. So if you look a little bit into the history of gravity, then there has been a decade-long debate actually whether gravitational waves exist, whether they are physical or whether they are just some gauge artifact. And that's quite remarkable because the first paper on gravitational waves, on these wave-like solutions, is from 1916 by Einstein himself. And we actually dig up that paper and put it on the wiki, at least the link to it on the wiki. But then, so there has been a very long debate until the 60s, 70s on whether gravitational waves actually exist. So, so general relativity in principle predicts the existence of gravitational waves. And it tells us something else, namely that the metric perturbations of flat space-time propagate at the speed of light. Yeah. So short gravitational waves propagate at the speed of light.
Helvi, you have 5 minutes.
Okay, yeah, that's perfect.
Question.
Yep, sure.
Yeah, so they propagated the speed of light. Is this something that relies on the assumption that we're working on a flat background, or does it work for perturbations about any background?
So if you do it carefully, you should see that gravitational waves in general relativity propagate at the speed of light. And actually, we will see that tomorrow when we look more closely at solutions. So again, we will work in a weak field approximation, but we will find solutions that show, that the waves propagate at the speed of light, which is not always true if you go to series beyond general relativity. Okay, yes, so let me just make one final comment before I stop. And then I would finish the second part of the gauges actually tomorrow, because even though we've ended up with a nice wave equation, we are not quite done yet. So if we count degrees of freedom, we will see that our original problem described by this metric perturbation h mu nu had 10 independent components. Now we applied our harmonic gauge, so we applied box x mu equals to 0, that reduces 4 components. So now we are at a stage where we have 6 independent degrees of freedom. As I already told you, we will see that actually we only have 2 degrees of freedom that propagate. So what I would do tomorrow is actually go through one more choice that we can make to really reduce our independent components to 2 to then properly describe gravitational waves. And with that, I would stop here. I would take more questions that you may have, and I will make sure to upload these notes tonight to our wiki if you want to go back to them. Okay, thank you very much.
Okay, thanks, Helvi. Are there more questions, more quick questions?
Well, maybe I can ask a question, but it's kind of a funny question. So you look in all the textbooks and everybody uses this trace reversed H, right? Because it makes the equation simpler. What's the physics?
Okay, that's an excellent question. And I invite you to look at the textbook by Poisson and Will, because they actually make a very nice connection between this trace reversed version of the metric perturbation and gravitational potentials.
Great. That's a book I don't own. So I'll get a copy. Thank you.
More questions?
I have a question.
Go ahead.
So you say you do a lot of numerics. How do you, what's the implementation of using this? How do you tell the computer how to do this?
Okay. So numerical relativity in a nutshell. So I actually don't use this weak field approximation. So I solve for the full metric. And what I do is I take my 4-dimensional space-time and I foliate that into 3-dimensional spatial hypersurfaces that are a function of time. Now, if you do that carefully, you can write Einstein's equations as a set of hyperbolic equations, time evolution equations for the metric, and a set of elliptic equations, set of constraint equations. So if you want to think about an analogy, take Maxwell's equations in 4-dimensional notation and split them up again into something that is time evolution equations in 3 dimensions. So there you have a very similar structure, that you get a set of time evolution equations for the electric and magnetic field,
and constraint equations. So something similar you can do for Einstein's equations if you split up this beautiful space-time structure into a time evolution problem. And once you have that, you would use these constraints to construct initial configurations that describe your physical system. So for example, 2 black holes or 2 neutron stars. And then you you implement evolution equations to solve for the metric at each time step. And then you actually look, or you can construct, for example, the Newman-Penrose scalars, which are contractions of the Riemann tensor with a null tetrad, far away, that gives you a measure for the gravitational wave. So you simulate the strong field regime by really evolving your strong field metric, so you're not doing a weak field expansion, and then you're computing Newman-Penrose scalars far away from, medium far away from that source. And to do that in 3+1 dimensions, you typically need high performance computing codes to do that.
Cool. I have 2 more follow-up and then I'll shut up.
Mm-hmm.
How do you program this into your computer?
So I'm actually using and developing a publicly available code that's called the Einstein Toolkit, and that uses C, C++. Some older components of the code still even use Fortran, and then you parallelize it with MPI. And if you're interested, so we actually have a school for PhD students, for new users, for the Einstein Toolkit. So if you're interested to using that, just maybe send me a message and I can send you the link to the school.
Great. Let's see here. There's one more. I forgot my second question, but thank you.
Okay.
Okay. Let's thank Helvi and we can stop the recording.
Mm-hmm.